Okay, one sample t-test in SPSS. I have a whole bunch of data in here, but the only ones we're going to look at here is age, gas, and protein. These are the ones we did in class. Age, click Analyze, Compare Means, one sample t-test. Click that. If you'll recall from in class, the test value that we had for that was a 2. So we'll enter a 2 here. This was about, we thought the age of daycare kids on average would be 2. We got our sample of 3 kids, not a very big sample, and it was one was 1, one was 3, one was 5. And so we're going to compare that to our test value of 2. Put 2 there, put age over here in the test variable, and click OK. Okay, so our statistics here, we have an N of 3, obviously. The mean was 3, so it's not 2. Is that going to be a significant difference? We'll have to wait and see. Standard deviation was 2, and that standard error, the mean, SEM, was 1.15-ish. Our t-statistic is 0.866. The degrees of freedom for this one is going to be n-1, so 3 minus 1 is 2. We'll see that the p-values are much higher than 0.05, so this is not going to be a significant difference. The test value is a 2. The mean minus that test value is 1, so there's a mean difference of 1. And then the confidence intervals, we talked about how to create those in class. These confidence intervals are, because it's a very small sample size, but we can talk more about that on the next example. If you wanted to, you could go to that appendix, appendix B, I believe, and you could look up the degrees of freedom. And let's say you had it set at 0.05, degrees of freedom of 2, and I can't remember what it is, maybe a 4.303, something like that. And obviously, in 0.866 is significantly less than that. Our next example was gas mileage. They had new cars coming out. They wanted to make sure that those gas mileage was going to be at least 45. Technically, you'd want that to be a one-tail test, but in the example in the book, they changed it to a two-tail, so we're just going to go with two-tail. But these, we have a sample size of 6, 40, 44, etc., and we want that, the hope is that that's going to be at least 45. So analyze, compare means, one sample t-test. Let's just click reset. We're going to move gas over, and then we're going to set that test value at 45. Click OK. N of 6, the mean was 43. Is that going to be significant? We'll see. Standard deviation, the SEM. We have a negative 2.2 t statistic. Our degrees of freedom, again, n-1 for this one. If we went two-sided, it's not going to be significant, 0.076. If it had been a one-tail, which in this case it probably should have been, it would have been significant at the 0.05 level. Now, just FYI, again, we talked about this, I think, in the lecture. If you have to set it up beforehand, you have to decide if it's going to be one-tail or two-tail or 0.05 or 0.01. You can't do the statistics and then be like, oh, okay, well, it's significant at the one-sided t-tail, so that's what we're going to do. You can't do that. That's essentially a form of p-hacking, so you don't do that. Test value 45 minus 43, that's a mean difference of 2. And then we have our confidence interval. The confidence interval is going to be the mean plus or minus whatever the t critical value, that value that you get from the appendix B, times our SEM. And so for this example, we have the 43 plus or minus, that's our t critical value, 2.571, times that SEM. Again, you can get that from right here, 0.89443. And so it gives us 45.29 to 40.71. So what this means is that these are confidence intervals of 95%. We are 95% sure that the true mean population is going to be somewhere between 40.71 and 45.29. If we took, you could look at this as like as a standard distribution. If you go out and get this sample 100 different times, 95% of those samples are going to fall between that 40 and that 45. Those are essentially like, if we think about the standard distribution with the z-scores, these scores right here at this listing are essentially like 1.96 and negative 1.96. And we're capturing 95% of what the distribution is. Okay, one more. These are protein bars. We suspect that the protein is supposed to be about 20 grams per protein bar, and so obviously there's a bunch of variation there. Let's see if it's significantly different though. Compare means, one sample t-test, we'll reset it, we'll move protein over, and then we'll set our test value at 20. In 31, the mean is 21.4. Got your standard deviation, your SEM. Our t-statistic is a 3.067. That's definitely going to be significant at the 0.05 level. It could have been significantly more, significantly less, so we probably would have set that at a 0.05, or we would have set that as a two-tail, 0.05. So this is what we got. So now you can say p is less than 0.01. And we have our confidence intervals. How you would write this up. So like in the gas mileage, our sample was lower than 45, and you'd list the mean and the standard deviation, but the difference wasn't significant. We're going to list those confidence intervals, which again you can do them by hand, or you can get them from the table here, -4.2 to 0.299. You list the t, followed by the degrees of freedom, equals whatever that t statistic is, and in this case it was p is greater than 0.05. That's for the gas. For the protein bar, I've included here the SPSS output, and so you're going to list the mean, 21.4, it's right there, 2.54 for the standard deviation. Our confidence intervals are a 0.47 and a 2.33. T, the degrees of freedom, n-1 in this case, being a 30. Our t statistic, which is 3.07, and p is less than 0.05. And again, if you wanted to, you could write that up as 0.0. You can, okay, yeah, let me rephrase this. You can set that alpha at 0.05 or 0.01, and then when you get the data back, if it is less than 0.01, even though you set it at 0.05, you can list it at 0.01. You just don't want to actually change the alpha level before, after you've collected the data. But you can, there's a little bit of leeway on how you can report that p-value. Generally, it's going to be less than 0.05, 0.01, or in some cases 0.001. Okay, I think that's it.